Okay, so this is help for chapter 14.5 through really the end of the chapter. What we're going to start talking about is latent heat. It's the first thing we're going to talk about. And this is essentially the amount of energy or heat that has to be added to a system in order for a phase change. So what you may or may not be aware of is that when, for instance, when ice is melting, okay, it has to be at its melting point, which would be 0 degrees Celsius. But then while that ice is melting, and until all of that ice has melted, the system isn't going to increase in temperature, meaning that we'll have a place or a time when it's all held constant at 0 degrees Celsius. And looking at this diagram or this box here, you can see that right through this region here, where I'm drawn in black, that the temperature isn't increasing. That we're having a flat spot. We're still adding energy into the system, but as we add energy into the system, the ice is still not raising temperature because it's still in the process of changing phase. This is what we call latent heat. And then once it's all become water, then we'll see an increase in the temperature. And again, when we get to that boiling point of 100 degrees Celsius, we get a solid temperature that never moves until we have added enough heat to change phases from water to steam. Then when it's all steam, we can continue to increase the temperature. So this process right here where we have these flat sections, this and this, these are where we talk about latent heat. And so latent heat is that heat required for phase change. Now a couple things are important. You have to be at the right temperature in order to cause that phase change. And so oftentimes we're going to have problems where we'll enter the problem maybe right there at say negative 25 degrees Celsius and we ask about melting ice. Well, that means we're going to have to change the temperature here first. So there's going to be some Q added. Okay. Last time we did Q equals MC delta T. That's still relevant anytime we have to change the temperature. But then once we've changed the temperature, the formula for this flat section is Q equals mL. The amount of heat we have to add is equal to the mass of the material times what's called its latent heat. Now there are two types of latent heat. Let's take a look at those two types. Here on page 392 there are two values we're going to work at. First off, I want to point out that we're not using the calorie values, so I'm scribbling these out. I don't want to look at those. It's just a kilocalorie version instead of a joule version. But on this table, it's really, really helpful. A couple things that are important. One is that we need to know at what temperature stuff melts and at what temperature stuff boils. Because if I want to melt ice, I need to know that it melts at 0 degrees. Because if it's not at the right temperature, I have to get it there before I can do any latent heat calculations. So it's important that you know the boiling points. So if I boil ethyl alcohol, it's at 78 degrees Celsius. If I boil oxygen, it's at negative 183 degrees Celsius. These numbers matter because they tell me if I still have to change the temperature first. That Q equals MC delta T. Then the other thing that's an issue here is that when we read these two table values, we have to remember that they are kilojoules, which means all of these need an extra 3 zeros. They're all in the thousands. And that's true over here as well. Okay, so first off, you have to understand that we're adding a lot of energy here when we talk about the heat of vaporization and the heat of fusion. Now fusion, if you think about fusing, is about solid, so there must be a solid involved. That's solid to liquid or liquid to solid. This is important because whether I'm freezing ice or melting ice, this is the amount of heat removed or added to produce that. And then over here we have vaporization, which means we are involving a gas. Notice that the gas numbers are a lot bigger than the fusion numbers. So vaporization is a lot harder than fusion is. And if we actually go back and look at the diagram, look back at the diagram, you'll notice the section where we have water and steam, that flat section, is significantly wider than the section in blue where we just have the fusion. It's much, much less energy to to freeze something than it is to make it condense or to make it turn to a gas. All right, so that's how we're going to use that table, and that's going to allow us to make some really cool calculations. And so, for instance, if we're looking at something like, you have 20 kilograms of ice at -10 degrees Celsius, and you want to turn it into liquid water, call it liquid, and you want it to be at 10 degrees Celsius. So we want it to be not freezing, but not room temperature, right in the middle somewhere. As we do this, we have to recognize first that the ice is not going to turn into liquid water until it's at 0 degrees. So first, we have to prep the ice by getting Q equals mc delta T. Now mass is the 20 kilograms. C for ice, we'd have to look at the table on page 286, or it's 380 something. No, we'll have to go back and look. 387, I think, is the page number with our specific heat values. And then the temperature change, that's 10 degrees, okay? That's how much temperature change we'd have to have there. Now it's at the melting point. So to melt, to actually physically melt, we'd have Q equals mL. Again, mass, and then L is the latent heat of fusion for ice, or for water. And then here, once it's melted, we still wanted to raise the temperature again. Q equals mc delta T. Again, there's only 10 degrees here, but our C is different because before it was ice, now it's water. And if you look at that table, we probably ought to take a quick second and take a peek at it. See, oh, there it is. You'll notice that water is broken into 3 categories. And even though these are random these are specific values for a specific temperature, we can use them for ice, liquid, and steam, 2100, 4186, and 2010. So as we look at those, obviously changing temperature is going to be different for each of those. Okay. That being said, the last 3 ideas are how do we transfer heat generally. The first option, 14.6, is conduction. This is when heat physically travels through a medium that is solid. So we're talking about a metal rod or a piece of wood. It's by physical contact of particles. Okay, and so these solid objects have vibrating molecules and atoms, and they push on each other to heat one another up. And that transfer of heat, it's a little like dominoes. Okay. And here we have a really cool model of what we mean by heat conduction. As we see heat going from the high temperature to the low temperature, obviously think of it a little like a river, and the bigger the difference in the temperatures there is, the steeper the river would be, or the steeper the grade would be, so we'd see a faster flow. In this equation here, we have Q over T, that's joules per second, which means it's measured in watts. Okay, that's kind of its unit. K comes from this table here, but we're only going to look at the joule column. We're not going to look at the calorie option because we're focused on joules in this class. Area is its cross-sectional area. So if you think about it, if it's circular or if it's a rectangle, whatever it is, the wider that opening is, the more heat can flow through it quickly. T1 minus T2 is the temperatures. And you really need, while it is true you could use negatives and you could use Celsius, technically the degrees don't matter as long as you make sure you always get a positive. Okay? If you're getting a negative, you're doing them backwards. It's always going to flow from high to low, so it's important you just make sure that you're getting a temperature that's a positive. And then L is the length or the distance between the two. So the further they are, the longer this rod is or things like that, the more it's going to affect how slowly heat will transfer. Okay. This is why on a cold floor, you'll feel the heat being pulled from your foot, whereas a rug, you don't. And it has more to do with the way that heat is flowing away rather than the temperature. Okay. So just keep in mind, temperature that we feel with our bodies is not the temperature that we measure outside. When we feel with our bodies, what we're feeling is the removal or addition of heat to our skin. And that is really about heat flow and conduction. It's not about temperature. So that's really important as a conceptual piece to understand that when I say it's cold outside, I'm feeling the heat being pulled from my body. I'm not actually gauging the temperature. Now, over time, I can get to a place where I have a sense, yeah, okay, I get it. I know it's about this cold outside. But that's from life experience. That's not so much that I'm a thermometer. The next type of heat transfer is through convection, which is when a fluid, typically air or water, flows and moves, warm, starts to go to the top, because as it gets warmer, it expands and becomes less dense. Less dense stuff tends to float, and so it goes upward. Then it cools, condenses into a tighter package, and then it becomes denser and falls down below. So you can see a couple of models of how that works. Radiation, or radiators giving off heat, and how it cycles in the house. The last one is radiation. And this is how the Earth warms and cools itself. Through most of the Earth's, what we feel during the day, that radiation that we receive from the sun, it sucks in during the day, and then at night it radiates that back off into the atmosphere, and hopefully we're able to radiate that out into space. We don't want to continue to add more heat than we give off, or the Earth will continue to heat at an ever-increasing rate. So it's important that the Earth is able to give off heat just as it takes heat in. And so we have this equation for finding the rate at which heat is radiated away from an object. And we have this equation right here that tells us that the heat exchange rate, so again, this is measured in watts, okay, because it's joules over seconds, it's equal to, this is called the emissivity. It'll be between 0 and 1, somewhere in there. It's basically telling us how good is this at emitting and receiving radiation. If something's good at taking radiation in, it's good at sending it back out. And you'll see that's always between 0 and 1. Things like black surfaces, like charcoal, have an emissivity close to 1, whereas a shiny piece of metal is going to have an emissivity close to 0, because it's really bouncing that heat back off. It's not absorbing it. The next thing we have is what's called the Stefan-Boltzmann Constant, which is just this number right here. Okay, it's a universal constant that just seems to pop up in different places, but it is always going to be that 5.67 times 10 to the negative 8 watts over meter squared Kelvin to the 4th. Now this unit, it's really interesting, because at the end of the day, it's about making the equation work. And so because it's divided by meter squared and Kelvin to the 4th, that has everything to do with these two guys. Turns out that because it is an inverse variation, we notice that we can divide by these units to create this constant sigma, which is our Stefan-Boltzmann. This is important, it's not the cross-sectional area, it's surface area, which should make sense based on the fact that we're dealing with something radiating. It would radiate from all of its surfaces. And then temperature to the 4th, it's really important that we have it in Kelvin. Okay, we don't want any negatives in there, but also, guys, it says K to the 4th. That should tell us we're using a Kelvin for our temperature. You wouldn't want to assume that negative 20 degrees Celsius and positive 20 degrees Celsius are going to radiate at the same rate. One is much colder, has much less to radiate off. Because remember, heat goes from high temperature to low temperature. We're not going to have it the other way around. Okay, hopefully that's everything you need, and we'll see you in class.